Imagine if an unknown beast existed on the wide, barren surface of Mars, a creature capable of destroying advanced technology, such as the Mars Rover. This alarming possibility is more than just science fiction, it's based on recent reports that have sent shockwaves through the scientific community. As we push the boundaries of space exploration, Mars mysteries only become more unsettling. Join us as we explore the significance of this revelation, considering its potential implications for our plans to populate Mars and how it could reshape our understanding of life's fundamental nature. The Mars Rover missions, especially those launched by NASA, have revolutionized our understanding of the red planet, transforming planetary science. Beginning in the early 2000s with the Spirit and Opportunity rovers, this series of robotic missions has paved the way for groundbreaking exploration. Launched in 2003, these early rovers were tasked with examining Mars' geological history, particularly in the context of water. Since water is essential for life, it has been a primary focus of most Mars missions. Both Spirit and Opportunity found compelling evidence of past water activity at their respective sites, Gusev Crater and Meridiani Planum, revealing some of the earliest signs that Mars once had environments that could support liquid water. Following these milestones, the Curiosity rover, launched in 2011, took Mars exploration to a new level. Its mission went beyond searching for signs of water to assessing the planet's habitability and its potential to have once supported microbial life. After landing in Gale Crater in 2012, Curiosity began exploring an area that scientists believed had once been a lake. Equipped with the Sample Analysis at Mars (SAM) laboratory suite, Curiosity could analyze Martian rocks and soil by drilling into them and identifying organic molecules, a critical indicator of possible past life. Additionally, Curiosity's ChemistryCam, which uses laser pulses to vaporize rock samples and analyze their composition, enabled scientists to study the Martian surface's chemical history in unprecedented detail. This laser-induced breakdown spectroscopy provided new insights into Mars' mineral composition and climate history. NASA has made substantial advances in rover design across its Mars missions. Spirit and Opportunity, for example, were powered by solar panels, which limited their operations due to dust storms and reduced sunlight in winter. In contrast, Curiosity was equipped with a radioisotope thermoelectric generator, RTG, allowing it to operate continuously without relying on sunlight. This innovation enabled Curiosity to function under diverse conditions and collect data throughout Martian seasons. Curiosity's suspension system, known as the rocker bogie, allowed it to traverse challenging terrain, climb slopes, and investigate difficult-to-reach geological features. Its robotic arm, equipped with drilling and sample collection tools, provided scientists with rock samples from various Martian formations. The next stage of Mars exploration began with the launch of the Perseverance rover in 2020. Designed to build on Curiosity's successes, Perseverance's primary goal is astrobiology, specifically the search for signs of ancient microbial life. With new scientific instruments, Perseverance includes Sherlock and PIXL spectrometers, which can map organic compounds and minerals at a microscopic level. Perseverance's SuperCam, a more advanced version of Curiosity's ChemistryCam, allows for rock analysis from a distance and has additional imaging capabilities. Another innovation is the Mars Oxygen In Situ Resource Utilization Experiment, MOXIE, an instrument that converts carbon dioxide from Mars' atmosphere into oxygen. MOXIE represents a crucial step for future human exploration of Mars, demonstrating the feasibility of producing life-supporting oxygen on another planet. Perseverance also carries Ingenuity, a small helicopter that has achieved the first powered flights on another world. Ingenuity's flights have proven invaluable for testing aerial exploration and giving scientists a bird's-eye view of Mars' landscape. Its ability to scout areas in advance has played a pivotal role in planning safe and efficient routes for the rover, setting the stage for future missions that might include similar flying vehicles to explore areas inaccessible to traditional rovers. However, Mars exploration has faced many challenges. Harsh environmental conditions, extreme dust storms, and the technical difficulties of remote operations from millions of miles away have posed significant obstacles. Dust accumulation on solar panels, for instance, can significantly reduce energy production, as seen with the Opportunity rover, which ceased operations in 2018 after a planet-wide dust storm. The immense distance means engineers must design rovers with considerable autonomy. Curiosity and Perseverance have autonomous navigation systems that allow them to make real-time decisions for obstacle avoidance, terrain assessment, and safe pathfinding, minimizing the need for constant commands from Earth. This ability to navigate autonomously has extended their operational ranges and improved mission efficiency. The rovers have not only transformed our understanding of Mars geology and climate but also shifted the focus toward potential human exploration. As Mars exploration progresses, NASA aims to return Martian samples to Earth, and the Perseverance rover is central to this goal. Perseverance is equipped with a sample caching system to store rock and soil cores, which a future mission, in collaboration with the European Space Agency, ESA, may retrieve. Bringing these samples back to Earth would allow scientists to conduct complex analyses beyond the capabilities of rover-based instruments, potentially unlocking deeper insights into Mars' history and its potential for habitability. During a routine examination of rough, rocky terrain, the Curiosity rover encountered a situation that prompted an alert from mission control. As it traveled over the rugged landscape, its sensors detected unexpected anomalies in the soil. Instruments provided inconsistent feedback, causing engineers to halt operations and investigate. Initial assessments revealed that Curiosity's wheels and sensor modules encountered unusual resistance, while its imaging systems detected previously unseen abnormalities in the Martian soil. Curiosity's location at the time, an area with rocky outcrops and fine, powder-like soil deposits, was thought to be a promising geological site. Yet, the soil's peculiar properties seemed to change as the rover approached, behaving in ways not documented on previous missions. Data from Curiosity's ChemistryCam and soil analysis instruments indicated a rapid shift in soil density and cohesion, as if the ground itself were moving or reacting. The rover's arm, equipped with instruments for drilling and sampling, struggled to maintain stability, and initial tests suggested the soil might contain elements or compounds previously undetected in Martian regolith. These unexpected changes raised the question of whether Curiosity had encountered a phenomenon related to subsurface activity, or even an interaction with an unknown biological entity. Although Mars is not known to harbor any current life, past evidence has hinted at the microbial potential in ancient, water-rich regions. Researchers studying the strange patterns captured by the rover's cameras noticed that the disturbances resembled formations influenced by external forces. These shapes appeared too uniform to be random, yet were unlike anything typically resulting from Martian winds or weathering. These symmetrical, repeated formations raised the possibility that something unusual, perhaps even mobile, had disrupted the soil after the rover's arrival. As the scientific community analyzed the images, several theories emerged. Some scientists speculated that the disturbances could result from volatile gases escaping from beneath the Martian surface, causing the soil to shift in unexpected ways. Such gas emissions might also impact the rover's sensitive instruments, creating unusual formations. Others suggested that mineralogical changes in the soil, perhaps triggered by temperature fluctuations or magnetic interactions, might explain the anomalies. Certain magnetic compounds, like magnetite or hematite, have been detected on Mars, and under specific conditions, they could create repellent forces that could explain some of Curiosity's observed malfunctions. Another hypothesis considered the potential role of unknown electrostatic forces on the Martian surface. Mars's thin atmosphere and lack of a global magnetic field expose it to significant radiation and solar wind. Under certain conditions, Martian dust and soil particles might gain unusual electrostatic charges, potentially interfering with the rover's electronics and sensors. This might account for the irregular feedback received by mission control and explain the visible soil disturbances. Meanwhile, a smaller, more speculative faction within the scientific community is exploring the possibility of microbial or biological interactions. They hypothesize that, while unlikely, some form of extremophilic microbial life might exist deep within the Martian crust, potentially emerging sporadically or responding to environmental stimuli. If microbial colonies interact with surface materials, they could form clusters or trails resembling organic patterns. Curiosity's instruments, though not specifically designed for current life detection, could offer indirect clues, especially through its spectrometers and laser-induced breakdown spectroscopy (LIBS) tools, which may reveal unusual organic compounds. This incident has cast a renewed spotlight on Mars as a dynamic and, in some ways, still mysterious world, with environments that may hold more surprises than previously assumed. The strange interaction between curiosity and the Martian soil opens up a range of scientific questions about Mars's geological and chemical processes and its potential for hosting or having hosted life in some form. The recent discovery of potential lifelike forms on Mars has stirred new debates about the planet's ability to support life. For decades, the scientific community has primarily hypothesized about microbial life, suspecting that any Martian life would exist in extremophilic microscopic forms. However, the possibility of more complex organisms would challenge established theories of Martian habitability, hinting at a unique, perhaps independent evolution. Such a discovery would suggest that Mars once harbored, or still has the capacity to sustain, life, even if only in isolated regions beneath the surface or within rocky outcrops. If these forms do indeed exist, they could represent an entirely new ecosystem, distinct from Earth, adapted to Mars's harsh climate and atmosphere. With surface temperatures plunging well below freezing and limited liquid water available, any complex organisms would likely exhibit unprecedented survival mechanisms. This concept shifts the focus from imagining life merely as microbial to considering whether more advanced life forms could survive, if not thrive, in these extreme conditions. If this phenomenon is biological, the next pressing question is one of containment and contamination. For decades, planetary protection protocols have aimed to prevent Earth-based microbes from contaminating Mars, and vice versa. However, contact between Martian and Earth organisms, if Mars indeed harbors life, could trigger unforeseen consequences for both ecosystems. Earth microbes, if introduced to Mars, could potentially adapt, compete with, or even disrupt local life forms. Conversely, should Martian microbes or organisms come into contact with Earth systems, this interaction could introduce contamination risks that might compromise Earth's biosphere. This scenario presents ethical and procedural challenges to Mars exploration, especially regarding the deployment of future human missions. Protocols may need to evolve to ensure that both Earth and Mars are protected from possible interplanetary contamination. Researchers are exploring new sterilization methods and containment protocols for Martian samples to prevent any accidental cross-contamination. On the other hand, some scientists argue that what has been perceived as an unknown creature might actually be a remarkable geological feature unique to Mars's environment. The strange formations observed in the soil and on the surface could result from processes that do not occur naturally on Earth, such as rapid mineral crystallization reactions with Mars's thin atmosphere or volatile gas emissions from beneath the surface. Mars has experienced significant geological activity over billions of years, including volcanic activity, meteorite impacts, and tectonic shifts, all of which could play a role in shaping unique mineral structures. Additionally, Mars's extreme conditions may lead to interactions between the soil and atmospheric gases, creating patterns and features that, under certain conditions, could mimic biological characteristics. This raises the question of whether the observed phenomenon is a product of Mars's distinct mineral composition reacting to temperature changes, radiation, or other environmental factors, producing features that resemble organic life in appearance but are entirely geological in origin. To determine the nature of this anomaly, scientists advocate for advanced methods to deepen their investigation. High-resolution imaging, more comprehensive soil sampling, and spectroscopic analysis could provide new insights. Technologies like laser-induced breakdown spectroscopy, LIBS, which Curiosity and Perseverance already employ, help scientists analyze the elemental composition of Martian rocks and soil from a distance, revealing chemical signatures that could hint at biological or geological origins. Additionally, scientists are considering next-generation imaging techniques, including multispectral and hyperspectral imaging, to enhance understanding. Imaging technology that can capture more detailed data could soon enable scientists to distinguish between biological and non-biological material on Mars. Upcoming Mars missions, increasingly focused on returning samples to Earth, represent a potential game-changer in the quest for extraterrestrial life. A joint mission by NASA and the European Space Agency aims to bring Martian samples back to Earth within the next decade, which would allow for comprehensive laboratory analyses that rovers cannot perform remotely. By examining these samples in high-tech, controlled labs on Earth, scientists could explore the chemical and molecular structures within Martian soil in greater depth, specifically looking for biosignatures, indicators of past or present life. However, sample return missions come with their own set of risks, especially concerning containment. To avoid any contamination risk, scientists must ensure that Martian samples remain securely isolated. The recent news of Curiosity's unexpected discovery, potentially indicative of life forms on Mars, has elicited mixed responses from the scientific community. While some researchers feel exhilaration and an urge to dive into the implications of these findings, they are also mindful of the high stakes involved. If anomalies in Martian soil truly suggest biological life, this discovery could transform our understanding of life's existence beyond Earth, possibly demonstrating that life can emerge even in previously inhospitable environments. This revelation would prompt a fundamental shift in our understanding of the conditions required for life to exist across the universe. However, excitement is tempered by caution, as many prominent scientists stress the importance of careful, methodical analysis of the rover's findings. They emphasize distinguishing between biological and geological explanations, as misinterpretations could lead to unnecessary alarm or wasted resources. If actual life forms are present, researchers must consider planetary protection implications and ethical responsibilities, ensuring future missions prioritize astronaut safety and preserve Martian ecosystems. The public response to these developments has been intense, with social media and news outlets reflecting a surge in both interest and concern. Space enthusiasts are thrilled by the prospect of extraterrestrial life, while others express anxiety about the potential risks associated with such discoveries. Speculation abounds, with theories circulating about these unknown entities' nature, implications for human exploration, and broader questions about life beyond Earth. Concerns about cross-contamination, whether from Earth organisms affecting Martian ecosystems or vice versa, have fueled calls for stringent planetary protection protocols. Amid this whirlwind of excitement and caution, there is a collective acknowledgement of the need for deeper investigation. Researchers are advocating for advanced imaging and sampling techniques to unravel the mysteries of Martian soil, seeing this quest as not just a scientific endeavor but a reflection of humanity's innate curiosity and desire to explore the cosmos. This debate underscores the balance between incredible potential and profound responsibility in our pursuit of knowledge about Mars. Elon Musk's vision for humanity as a multiplanetary species has captivated millions, with Mars as his primary goal. Musk's intentions reach far beyond exploration. He envisions constructing a thriving city on Mars, equipped with the infrastructure needed to support human life. His plan involves sending fleets of SpaceX starships, each designed for long-duration space travel, to transport thousands of residents to Mars. This ambitious concept imagines self-sustaining communities that utilize Martian resources to create an environment suitable for human habitation. The idea of colonizing Mars has sparked a wave of interest and investment in space technology, reflecting a growing optimism that life on Mars could soon transition from science fiction to reality. However, recent discoveries suggesting the potential presence of unknown life forms or hazardous environments on Mars present significant challenges to Musk's vision. If biological entities exist on Mars, they could introduce unforeseen complications to colonization efforts, necessitating a re-evaluation of timelines and strategies for human settlement. For instance, the risk of contamination, where Earth microbes might interact with Martian life or vice versa, demands a rigorous planetary protection approach. This could alter habitat designs to prioritize not only functionality and comfort but also the containment and mitigation of potential biological threats. Musk's goal of terraforming Mars to create an Earth-like environment may also require significant adjustments. Large-scale modifications to Mars's atmosphere or surface, intended to make it more hospitable for humans, could inadvertently harm any native ecosystems, raising ethical questions about our responsibility to protect possible Martian life. In light of these discoveries, Musk's plans might need to pivot toward innovative solutions that prioritize biological safety. Developing technologies to detect and neutralize potential biological threats could become essential, necessitating investments in biosafety and biosecurity measures. Habitat designs might evolve to emphasize resilience against both biological and environmental challenges, possibly including closed-loop life support systems that efficiently use Martian resources and ensure the safety of settlers. A flexible and adaptive approach to colonization could encourage cross-disciplinary collaboration, integrating insights from astrobiology, geology, environmental science, and engineering. This interdisciplinary research approach could make Musk's vision of Mars colonization more sustainable and ethically responsible. While the dream of Mars settlement continues to inspire, it now faces the complex realities of what such a future might entail. Elon Musk's vision of humanity as a multiplanetary species, with Mars as the focal point, has ignited widespread enthusiasm for space exploration. His plans go beyond mere exploration, aiming to create a thriving, self-sustaining city on Mars with all the necessary infrastructure for human life. Musk proposes using fleets of SpaceX starships, designed for long-duration journeys, to transport thousands of settlers to Mars, drawing on Martian resources like water ice, carbon dioxide, and regolith to develop a habitable environment. This transformative vision aims to shift Mars from a distant concept to a potential reality. Yet, recent revelations about possible unknown biological entities or hazardous conditions on Mars introduce significant hurdles to Musk's grand plans. Discovering microbial life or other biological activity could necessitate a re-evaluation of human settlement timelines and methods, with contamination risks between Earth microbes and Martian organisms or ecosystems becoming a primary concern. This would require stringent planetary protection protocols, and habitat designs would need to provide comfort and utility while also managing and containing any biological threats. Musk's goal of terraforming Mars to create a more Earth-like environment may also face reconsideration. The process of modifying Mars's atmosphere or surface could become more complex if biological life exists, with potential disruptions to Martian ecosystems leading to ethical questions about our responsibility to protect native life. In response to these findings, Musk's plans may need to shift toward innovative solutions that emphasize biological safety and security. Investments in technology to detect and neutralize biological threats could become a priority, ensuring that human presence on Mars does not inadvertently harm local ecosystems. Habitat design could evolve to prioritize resilience against both biological and environmental challenges, including closed-loop life support systems and efficient resource utilization. Encouraging interdisciplinary collaboration could allow Musk's Mars colonization vision to evolve into a more sustainable and ethically grounded endeavor. In this dynamic landscape, the dream of Mars settlement persists, but it now contends with the complex realities that such a future may entail. In light of recent discoveries, Elon Musk's plans may need to shift toward more innovative and adaptive solutions. Emphasizing the development of advanced technologies aimed at detecting and neutralizing potential biological threats could become a priority. This would involve significant investments in research focused on biosafety and biosecurity to ensure that human activities on Mars do not harm its ecosystems. Additionally, habitat designs may need to evolve, prioritizing resilience against unforeseen biological and environmental challenges. Developing closed-loop life support systems that efficiently utilize Martian resources and safeguard human settlers from potential dangers could prove essential. Moreover, fostering collaboration among diverse scientific disciplines such as astrobiology, geology, environmental science, and engineering would be crucial in crafting a sustainable and responsible approach to Mars colonization. By integrating insights from various fields, Musk's vision of establishing a human presence on Mars could evolve into a more viable and ethically sound endeavor, addressing the myriad challenges and responsibilities that accompany such a transformative journey into space. The ethical dilemma surrounding the question of whether to explore or not to explore becomes increasingly significant as humanity pushes the boundaries of space exploration, particularly with missions to Mars. We confront crucial ethical considerations regarding the potential discovery of extraterrestrial life. The quest for knowledge must be balanced with the risks of contamination and the responsibility we bear as explorers. Central to this discussion is the principle of planetary protection, which aims to prevent biological contamination of other celestial bodies and safeguard Earth from potential extraterrestrial microorganisms. Planetary protection encompasses a range of protocols designed to minimize the transfer of earthly microbes to Mars and other destinations. For instance, the Perseverance rover, which recently landed on Mars, underwent stringent cleanliness standards, allowing fewer than 500,000 bacterial spores on its entire payload and specifically limiting the number on the rover itself to just 41,000. This rigorous sterilization process included high-temperature treatments and the use of chemicals like hydrogen peroxide to ensure that the spacecraft did not introduce Earth organisms into Martian environments. The ethical implications of our explorations extend beyond the risk of contamination, challenging us to consider whether we have the right to explore and potentially exploit other worlds. Some scientists argue for a form of sanctification of Mars, suggesting that if we discover signs of past or present life, we should treat Mars with a level of respect akin to that afforded to protected environments on Earth. This perspective raises questions about our obligations to preserve any Martian ecosystems that might exist, advocating for strict guidelines to govern interactions with potential life forms. International cooperation is crucial for establishing a robust framework for exploration. The Outer Space Treaty, signed by numerous nations, emphasizes the need to avoid harmful contamination of celestial bodies. However, compliance with these guidelines often relies on voluntary adherence rather than enforceable regulations, leading to inconsistencies, especially with private companies entering the space exploration arena. The Committee on Space Research, COSPAR, has proposed varying levels of planetary protection requirements based on the mission's objectives and the potential for life on the target body, but these recommendations lack binding authority. As the landscape of space exploration evolves, the scientific community increasingly recognizes the necessity of an ethical framework that addresses these complex issues. The dialogue surrounding planetary protection must evolve alongside our technological advancements and ambitions, ensuring that we approach our celestial neighbors with respect and responsibility. Balancing our thirst for discovery with these ethical imperatives will shape the future of space exploration and our understanding of life beyond Earth. As we contemplate the potential consequences of an unforeseen factor damaging a Mars rover, we find ourselves at a crossroads in space research. The secrets of Mars may hold the key to understanding life beyond Earth, but they also test our goals and ethics. Will we be able to adapt our plans and strategies to meet the unique challenges of Mars, or will the enigmatic forces of the Red Planet prove too difficult for even the most advanced technology? As we venture further into space, one thing becomes clear: Mars is more than just a destination, it is a complex puzzle, inviting us to uncover its mysteries. Given these discoveries, we must ask ourselves if we are truly prepared for what Mars may reveal and what this might signify for our place in the universe. The answers could fundamentally reshape not only our understanding of life beyond Earth but also our responsibilities as stewards of our own planet and any others we may one day inhabit. The pursuit of knowledge is fraught with uncertainty, yet it holds the promise of discoveries that could transform everything we know. Share your ideas and speculations in the comments below.